Here we go. Thursday before an ultra long weekend. We got this. All the quizzes are done. I posted your last two assignments. They're both on regression. I don't know if you'll be able to do all of them after today, but probably the first one, like you can try them. They're open till next Friday anyways. So you got time, but that's it. That's all for assignments. So the end is near. All right. I was very pleased with quiz 4. So good job. I did mark hard, but then you'll be rock stars for the final exam. I know it. I can feel it. You've got it in you. Anything in the 30s was good. So we're really good. So, all right. We started regression. I really can't remember. We talked about, oh yeah, scatter plots. And to describing a relationship, we need to talk about 3 things, right? Shape, direction, and strength in some order. Okay, so the shape, I say shape, you could say form if you want. I know I've already complained about it, but my Apple Pencil is acting like it's running out of ink. It's very weird. It's weird. The tips must be getting tired or something. Or maybe I'm getting tired. Yeah, right. I think it's just the tip. Yeah. Yeah. So it's a weird feeling though, because I know it's not a real pen, but it's certainly acting like one in the worst ways. We're going to break it down into whether it's linear or nonlinear, right? And we're going to steer so clear of nonlinear relationships. Of course, we can model nonlinear relationships, but for us in this course and basically anything that we do is going to be linear. All right, so the shape, and I say shape because we use the word shape for histograms as well, right? Shape, center, spread. So a little bit different, but as few words as possible, I guess. The direction is either positive or negative. Right, and in terms of the direction, so positive or negative, right? I'll put little arrows on here just to emphasize it, right? And then the strength. Strong or weak. Feel free to kind of add, what are those, are they adjectives? Descriptors? Like moderately strong, moderately weak. A strong relationship is when you can clearly see a pattern, and a weak relationship is when they're just kind of all over the place. Right? Maybe I should. Yeah, so you can have a scenario where you have something that looks like this, right? Then you have a very strong non-linear relationship, right? And you can model this. You can model it, but we're not going to. We're not going to deal with anything that's non-linear. right? Because if we fit a line to this, it would look like this. And it would do an excellent job here and an excellent job here and just a terrible job everywhere else. So there are techniques you can transform the data if you wanted to and make it a line, if you can pull that off. But we're not going to deal with it in this course. It's always such a relief when you're reading a textbook or something and it says something like, it's beyond the scope of this textbook. Oh, phew, okay, just forget about it. All right, so the correlation we talked about. Correlation is a numerical measure of the direction and strength of a linear relationship. So it's a numerical measure of the strength and direction of a linear relationship. This is where I mention that we'll be able to calculate the correlation between any two things, so any two variables, but it only applies to a linear relationship, right? It's only useful for a linear relationship. So computers do what we tell them to do. And so that's where we come in and say, okay, well, yeah, I could calculate the correlation, but I shouldn't, right? Because it's not linear, right? It's one of those things. All right, so we said that correlation goes between -1 and 1. Here, 0 means there's no relationship. If it's negative, of course, you have a negative relationship. And if it's positive, you have a positive relationship. That part's fine. All right. And then we said, just as a rough guide, between -0.5 and 0.5, we'll call it a weak relationship. There's some artistic freedoms there that you'll have, right? If you tell me that it's a strong relationship, right, then fine, I'll accept that. Right? Not if it's less than 0.5 though. And then here we have a strong positive relationship. And here we have a strong negative relationship. So it's really important that correlation is between -1 and 1. Then, by request, we introduced R². I jumped ahead a little bit, totally fine. R² is the percentage of variability. I'll redefine it here. Is the percentage of variability in Y explained by the least squares regression line on X, explained by the least squares regression line on X. You can tell it's jumping ahead a little bit because we haven't truly introduced the least squares regression line, but it's the line of best fit. Okay. So here, least squares regression line is really the line of best fit. It's how we are going to calculate the line of best fit, and most commonly how we calculate it. What I usually tell my students, which is you now, when you see something like percentage of variability or proportion, right? A percentage is a proportion, right? Or fraction. Those are all synonyms, right, of percentage. And so the percentage of variability, as soon as you see I want you to have kind of an internal switch and say, okay, R squared, right? Oh, it's a really long definition, but if I tell you that 80% of the variability in Y, then you think percentage of variability, that's R squared. Okay, then I know what R squared is, okay? And calculator wise, calculation wise, I guess, the R squared is the correlation squared. So if you have the correlation between -1 and 1, if I square that, right, then it just takes the negative side, right, between 0 and -1 and makes it positive. And so now R squared is between 0 and 1, which is a percentage, right, or a proportion. Right, and so the correlation is between -1 and 1. But when I square it, right, the negatives become positive, and it just flips it to be between 0 and 1. Okay. For our problems, we're going to need the correlation. And so one of the ways that I could give you the correlation is if I give you the R squared. Okay. And so, because then what would you do? If I give you R squared is 80%, then 0.8 is the correlation squared. Then I would take the square root of 0.8, right? And then I would have the correlation. But remember, then we need to make it negative if it's a negative relationship. Okay, so I guess it's not really part of the review, but it just goes so nicely here. It's worth mentioning. So for our problems, we will need the correlation. One of the ways that I could give you the correlation is by giving you R squared. One of the ways I could give you the correlation is by giving you R squared. I'll say as well, because what else would you need? R squared is between 0 and 1, right? So it's positive. But then when I take the square root, it's just going to stay positive. So what do I need? I need to know what the scatter plot looks like. Because if you have a negative relationship, then you're just going to tack on the negative, right? And so as well as a scatter plot. To see which direction maybe what the direction of the relationship is. So for example, 80% of the variability in Y is explained by the least squares regression line. Regression line on X. What is the correlation? And let's say that the relationship looks like this. So then R squared is 0.8, right? Because R squared is between 0 and 1. But reported as a percentage, we've seen that a lot before. So you're no stranger to that. the correlation squared, but then when I take the square root, let's see here, I don't trust myself. Square root of 0.8. It is plus minus there. But usually I forget that 0.894427191. But because it's negative, right here, negative. So then here, that value has to be negative. So a little bit of extra work. Usually if I do something like this, it will be a negative relationship just to make sure that you are kind of keeping up with that. Yeah. Okay. I'm gonna go back and say the end of the review was there because that was all new. Sorry about that. Sneak it in there. Okay. All right. Kind of going rogue here. But a correlation of negative 0.894 means that we have a strong negative relationship, right? And we're assuming that it's linear. Sorry, what's the plus minus? When you take the square root, it's plus minus technically, but usually I forget it.
And then we kind of determine that we're like a negative value because it's a negative slope.
Yeah, so that's when you would need to be given the scatter plot, right? And then you can see that it's negative, and then you would just tack on that negative. Nice. It's a lot easier though if I just tell you what the correlation is, right? But this is one of the options. Okie dokie, artichokey. Let's see here. On your formula sheet, where is it? I give you these guys. Okay. So this is from your formula sheet. It looks big and kind of scary. There is one question on the assignment where I think you have to calculate the correlation using the sums. Okay. But I give you all the values and then you just need to find the sums and use them. That's just for practice. That's not on the final exam, right? So on the final exam, I either just explicitly tell you what the correlation is, or I give you the covariance, which is this SXY, or I give you the R squared, right? So there's kind of three options. But for us, we're going to focus on this formula for the correlation. The correlation R, lowercase or capital, doesn't matter. But for me, I'm so used to using lowercase that it got confusing. So I just can't do it. But so this is the one that we're going to be using on the final exam if you need to. Okay. This one is the one that you would use on that one on the assignment, just for practice. Okay. Lots of sums, nothing terrible though. But here, what we have is SXY is the covariance. Okay. So there's going to be a covariance. So at the very least, I give you the covariance. S subscript X is the standard deviation of X. And S subscript Y is the standard deviation of Y. This is where it's going to start to become very important that you keep track of which value is your X and which one is your Y, or which variable is your X and Y, right? Because in this case, when you're multiplying it, it doesn't really matter, right? Later it will when we deal with fractions, right? 1 over the other, 1 over 2 is different from 2 over 1, right? So it would make a huge mess. So you need to keep them straight. Okay. So given SXY, SX, and SY, we can calculate the correlation. Oops. Oh, whatever. There. I can't. Too messy. Oh. Okay. Just so we know where we're going, now I'm going way off script here. Oh, I don't know if it copied. Let's see here. No. Just because I want you to see where we're headed here. We're going to be building a least squares regression line, and a least squares regression line looks like this general form of a line, right? Y equals mx plus b is usually what we're taught in high school. For some reason, I don't know why we use that. Could be ax plus b or a plus bx, any of those combinations, right? But as soon as you have x and some value on its own, then it's going to be a straight line. Right. And I do want to talk about these components, but I also want to just show you that it's all on your formula sheet, right? And so here, the least squares regression line is going to look like this, right? And we're going to pick this apart, but then I tell you with a slope, right? So I tell you that B1 in this equation is, right? The slope, how you're going to find it is by taking that correlation. So this is where you're going to get a negative slope if you have a negative correlation, right? And a positive slope if you have a positive correlation, right? So that's where it's important to have the right sign on your correlation. Again, we see this standard deviation of y divided by the standard deviation of x. So now it's going to be so important that you keep track of is your explanatory variable and which one is your response, right? Then when you have the slope, then you can find the y-intercept, which is your b0 or b naught, but it needs the slope to find it. And we also need the slope times the mean of x and then the mean of y minus the slope times the mean of x. Okay. So it kind of goes like this. I think of it kind of like a pinball machine. So you've got the slope here, and then you find the slope, and then you use it here, and then you can solve for the y-intercept, which is b naught. So here, given the correlation, right? Either explicitly through r squared or by SXY, the covariance. And maybe what I'll do is I'll say the covariance and then in brackets SXY. Okay. right? So one way or another, you're going to have the correlation, lots of different options here. Okay, so you're given the correlation, you're given Sx and Sy. So the standard deviation of X and the standard deviation of Y. And the last two things that you need is the mean of X and the mean of Y, right? The sample mean of X and the sample mean of Y. Given those things, you'll be able to calculate, right, relatively simple math calculations here. So that's not something that we're worried about, right? It's more about the interpretation that we're going to get to, okay? But in the end, we're going to be building this regression line, okay? So let's see here. There are a couple of other things that we can do with regression, but usually what we want to do is we want to build a model so that we can predict future values. Now, when I say future, I don't necessarily mean in time, but I mean unseen values. Okay? And so the most common use of regression, it's kind of a new thought, I guess. Rarely indicate those in the notes though, I just kind of go for it. I've realized as I read through my notes, like, oh yeah, here was a different thought. Let's do this. We'll come back to that. I just want you to see that that's where we're headed. Okay. So the most common use of regression is to model a relationship and predict, so that's kind of a key word, predict future values, and I'll put future in quotes here, future values not necessarily in time, but unseen values. So what we're going to have, right, from our formula sheet is y hat is equal to b naught plus b1x. Right. The general equation of a line versus the general equation of a line we're usually told is y equals mx plus b, right? Or if you prefer to match what we have here, b plus mx, doesn't matter. Doesn't sound right though, b plus mx. It's mx plus b. We know that, right? But to match here what's going on here, because the b naught is on its own, okay? And just like here in the general equation of a line, the value that's on its own is the y-intercept. And remember, you have clues on your formula sheet, right? The value on its own, on maybe not apostrophe, on its own is the y-intercept. And the value attached to the x, maybe I'll use green. The value attached to the x is the slope. And you have those clues on the formula sheet. So I like to kind of guide you when I can. Okay. All right. So we're going to transition from y equals mx plus b, but y hat equals b naught plus b1x is the same thing, right? We have a y-intercept, we have a slope. And so when we're talking about y hat, oops, equals, not plus, equals b naught plus b1x, y hat, we've seen hats before, but that's when it was a sample proportion, right? So now when we're talking about regression, it's going to be purely by context, contextual, is that a word? Contextual? Oh, and I remembered what the word I was looking for. When we transform and then we, oh my gosh. Transform is what I said. Revert, right? You transform and then you revert to the original. Anyways, yeah, I'm falling asleep. I'm like, oh, revert. So purely by context, you'll know that a y hat is a predicted value of y. Because going back here, the most common use of regression is to model a relationship and predict future values, right? So I'm trying to predict values of y, and so that's why we denote it by y hat, right? The predicted value of y. And we said here, this is the y-intercept, which we know how to solve for, right? B naught is y bar minus b1 x bar. Just kind of throw everything into a pile here. And b1 is the slope. And b1 was r times, is it sy over sx or sx sy over sx? All right. So what we're going to have is we're going to have a value for the y-intercept, we're going to have a value for the slope, and then what we'll be able to do is we'll be able to plug in any value of x and calculate the predicted value of y. R. And you can use a capital R if you want. But I'm ruined. I can't. All right. So given a value of x, we can calculate y hat, which is what we are going to want to do. Let's see here. I'm gone completely off script, and maybe it's because I don't want to talk about residuals. All right, delayed gratification. If we do it now, then we don't have to do it next week and we can just have a fun week. All right, so let's do that. I am going to use that possum data. Wait, where is it? Where is it? Oh man, okay. And in this scenario, there he is, the brush-tailed possum of Australia. All right, so what we're gonna do is just remind ourselves of this relationship. I'm gonna bring that in. So going back to this possum data, and just in a fake scenario, we're just going to use this equation of the line. So we want to describe this relationship or model the relationship between the head length of the possums and the total length of the possum. Yeah. And so here we had y is the head length and x is the total length. In our blurb that we're skipping, right, I would give you the mean head length, the standard deviation of the head length, the mean total length, and the standard deviation of the total lengths, and then the correlation somehow, right? But let's just jump right into it. And I hate how they do this, but we could fit the linear relationship by I, which is just so weird. And then they figure out this exact formula for the fit by I. It's very weird. But let's say it looks like this. Maybe like that. I don't know. Hey, Emily, that's a pretty bad line of best fit by I, isn't it? Yeah. Yeah, one problem is that here, this isn't 0, right? So you can't work with that. Anyways, I've done my best. We just need it to showcase what residuals are. Okay, and so maybe I'll grab their fit by I. It's such a weird thing. Okay. And I get why they do it, but at the same time, I don't. Because what I'm preaching is don't do this. Don't fit it by I, but here we are. So y hat is 41 plus 0.59x. That's that line that they've fit. Okay. The reason they do it like this is so that they don't have to introduce how to calculate the slope, how to find the intercept, how to interpret those things yet. Okay, so that's what we're doing as well. Okay, so from each line or from each point, right, I'll pick one that they haven't picked, right? Let's look at this little guy here. It's going to be, maybe yellow was a bad choice. How about lime green? I never use lime green. How does it look? That's okay. It's kind of mustardy. Supposed to be lime green. I'll stick to pink, thanks. Okay. So this point is going to have some x value and some y value, right? That's just how points work. Which means that at that value of x, we have an observed value of y, right? But at that same value of x, what we could do is we could say, okay, well, actually, using the line, this would give me my predicted value of y at that value of x. So this is x and y hat. And so each point is at an observed value of x and y. We can calculate the predicted value of y at that same point of x. We can calculate the predicted value of y, which is y hat, oops. by using the same value of x in y hat equals, and in this case, 41 plus, let's see here, y hat equals 41 plus 0.59x. Now, I don't know what value of x it should be. What is it? There's 5 here, 187 looks a little, 86.5 maybe. I don't know, doesn't matter. But as long as you understand that, okay, I'm gonna have some observed value of y and some predicted value of y, right? Now the distance between these two values, right, the observed and the predicted value of y is called the residual. Okay. So the residual is the distance between the observed value of y, oops, and the predicted value of y. So we use E for the error because R was already taken with correlation. I suspect that's what happened, right? But E is the residual, but also the error, right? It's the error of that line. Yeah. So here, E is for residual or error, right? Emphasizing the E. I have a subscript I because every point is going to have some residual, right? It's some distance from the line. Sometimes it's small, sometimes it's big. But the residual is going to be yi, which is the observed value of y, minus yi hat, which is the same as observed minus predicted, is usually what I end up saying in my head, right? Observed minus predicted, of course, it's the y's, right? Because it's at the same value of x. Okay. Every point in our data set will have a residual, right? And the residuals can be positive or negative, right? It's negative if the values are below the line, but now if I look at a value above the line, right, my observed y is, let's say, 98, and my predicted y is 90-ish for this point here, right? Then it'd be 98 minus 90, so then it's positive, right? Whereas this one here, the observed value of y is, I don't know, 86, 87, 88, final answer. I don't know, I'm just guessing. Minus 90, right? So if they're below the line, they're negative. If they're above the line, they're positive. But you can kind of get there just remembering that it's observed minus predicted. Okay. So every point in our data set will have a residual. Okay. What's kind of fun is it's kind of like the snake eating the snake, or I don't know, I guess a kind of a catch-22. So how we fit the line is by minimizing the residuals. In fact, we minimize the squared residuals, and that's where the least squares regression line comes from, okay? But how can you minimize the residuals if you don't have a line, right? We need a line to find the residuals, but then the line of best fit is the one that minimizes those residuals, right? And so it makes sense, right? You want to minimize the distances overall. In fact, the sum of the residuals, because of how we fit the line, the sum of the residuals will be 0. Okay? And so when we fit a line, or when we fit a linear regression model, let's get fancy. We typically, and this is kind of across the board, it would be weird to use anything but we typically use a technique called least squares regression. And right, least squares regression is just linear regression. If you prefer to call it that, right? But technically it's a least squares regression, okay? And the least squares regression comes from, we fit the line that minimizes the squared residuals. Okay? And so we fit a line that minimizes the sum of the squared residuals. Notice that it's squared. Why? Because of how we fit the line, right? By minimizing the sum of the squared residuals, the sum of just the residuals will be 0. Okay? So here's a fact, or I haven't done an LFF in a while. Little fun fact. The sum of the residuals is always 0. Okay? But here we're minimizing the sum of the squared residuals. So there are two main reasons why we use the squared residuals, right? Because we're gonna have some negative, some positive, right? And so we use the squared residuals for 2 reasons, or there are others, but 2 main reasons. We had to deal with, okay, positives and negatives, obviously because of how we fit the line, they're going to add to 0. So I need to make my negatives cancel out my positives. And so one way to do that would be to square them, right? Squaring negative values makes them positive. Alternatively, there is a method where you just take the absolute value, right? That's also a way to turn a negative into a positive, right? But the follow-up to that, why we don't use the absolute value, is because when we square it, right? If I take a residual of -1, right? I square it, becomes +1, right? And so now it's just positive. But if I take 2, so -2, I square it, it becomes positive, but +4, right? And so now I'm amplifying these larger distances, right? Because I need to get my line to kind of go and minimize those residuals, okay? And so the first reason is that negative residuals become positive. Okay. And the second reason is that it amplifies large residuals. But so if you are kind of test driving a line, because that's what it does in the background when it fits a line of best fit, is it says, okay, fine, I'm going to try to fit a line, I'm going to calculate what the residuals are, and then I'm going to readjust, right? And that's where we landed. But what it does is if it finds that there are large residuals, it says, okay, can I minimize this, right? Can I try to capture those instead? So then it becomes kind of a line of best fit, if that makes sense. I would think of it as starting with a slope of 0 and then kind of adjusting to make up for those large residuals. It's not something that we need to worry too much about, because we are just going to have the formulas and use them and then interpret them. So we're not going too far, but it amplifies large residuals, right? And tries to capture them. Okay. All right. So what we're going to do is we're going to pretend that we've already fit a model, right? So found the slope, found the intercept. And of course, we can use R to very easily fit a linear model, but it requires data. So I didn't make a little R thing in the assignments for this one because I got lazy and I didn't want to give you data to work with, because it's kind of limited in its capabilities, but kind of fun to play around with. You can use the LM command. You've probably used it before, and it just does it. But it is using the least squares regression line. Now, to assess a model, right, how well it fits the data, we conduct a residual analysis. Oops. A couple of different parts of a residual analysis, and I don't want to spend too much time here because it's not on the final exam. It's just one of those things that I need to talk about. Then we can, it's on your assignment, but it's not on the final. Okay, so the residual analysis, because there's so many components, you'll probably need to do it in, if you take Stat 310, you'll do it more thoroughly with Claude, but because it is a huge part. But for us, at this point, I just need to get everything that's on the final exam onto the plate, so to speak. If you watch Food Network at all, get it on the plate. So residual analysis, we're going to have a list of residuals, right? So what we said was each data point, right, in our data set, which think of a spreadsheet, right? I'll have some observed Y, I'll have the line, so I'll be able to find the predicted value of Y, and I'll be able to find the residuals. Now, if you're using the LM command, once you have fit the model, you can extract the residuals, you can extract the fitted values, so they're already in there, right? It just calculates them. What we're going to be looking for, right, is our residuals should be approximately normal. We know how to do that, right? I can fit a histogram, I can look at it, does it look approximately normal? I can use a QQ plot, right, going way back, which fits the observed and the expected values. And then if it fits a diagonal line, then it's a normal distribution. So here, first we need approximately normal residuals. Oops. I will add centered on 0. What can we do to check that? You can make a histogram and just look at them. You can make a QQ plot. Got lots of options. QQ plot. Quantile plot. Also fun to say. So that one's not too bad. The second thing that we're going to look for is constant variance in the residuals. We remember the equal variance conditions from the ANOVA. And what would you know? We will use ANOVAs, but for the coefficients for multiple regression if we get there. So it is going to come back, but for now, we're just going to look for constant variance in the residuals. Variance meaning spread, right? This looks like variance, so I'm going to change that. Variance. And we're also going to use the same plot to check for linearity in the residuals. Okay, these two we're going to be able to check with residual plots. Check with residual plots. Okay. And now a residual plot looks like this. You're going to have your residual on the y-axis. And depending on kind of what you're doing, usually we put the explanatory variable down here, but sometimes it's the fitted value. It kind of depends, but for us, let's say it's always the explanatory variable, just for simplicity's sake. Okay. So the new thing here is that the residual is on the y-axis. Okay. The residual has to be centered on 0, which means that what we're looking for in a residual plot, right? So this is a residual plot, puts the residual on the y-axis, okay? And what we're going to be looking for is just random scatter around 0, random even scatter around 0. We look for random even scatter around 0. Okay. Then we have a well-fitting model, right? This doesn't look like 0. There. Yeah. Okay. So here, the residuals have to be centered on 0, so that's why it has to be random scatter around 0. The constant variance is the even scatter, right? So we're looking for even scatter, and then the linearity is that just a random scatter, right, all around the line at 0. Yeah. So what we're going to find is that the residual plot, and this is what kind of had me very confused when I was first doing residual plots, And so if it's confusing, you're not alone. The residual plot is basically a magnification of the original scatter plot. So it's not really going to give you anything new, really. But the residual plot magnifies any issues in the original scatter plot. So we might have missed any issues. So then when we make the residual plot, then we'll be able to pinpoint those issues. Now let's see here. So a residual plot looks something like this. So here you've got the original scatter plots. And then down here you have the residual plots. Okay. So here in this first plot, I'm going to zoom in. Okay. The original scatter plot, when I look at this, I say, okay, it looks good. It looks like I should be able to fit a straight line and it's going to do a reasonable job. And the residual plot, right, there's usually a line at 0 or we add a line at 0. And it looks like I have random even scatter around 0. So it looks like I have approximately normal residuals because that's what the random scatter, the random even scatter makes a normal distribution. Okay, and so that's good. I have constant variance, right? Because I have kind of this even band. So I have all the conditions are met, right? And linearity, it's a straight line around 0. Good. So this one is all good. I wish I didn't have a page break here. Hate that. Okay, that's okay. Let's go to the next one. So you're looking at this scatter plot, the original scatter plot, and you're thinking, okay, probably fine, right? I can fit a straight line to this. And so, but then when we look closer, we see that, okay, maybe we shouldn't. I wouldn't be this picky, right? But really we shouldn't fit a straight line like this, because what happens with our residuals is we have this very not random scatter around 0, right? They're still centered on 0, about half of them are below, half of them are above, right? But now I have this non-linear pattern, right? And so then the linearity condition is not met, right? Okay. So then if we look at the next one, the last one, what condition is going to be not met? Probably the constant variance. So here we have this kind of cloud and we said, okay, well, I don't see any other pattern here, right? So I'm going to fit a straight line to it. That's fine. But what's going to happen is we've got this kind of funnel pattern. Now it's not super obvious here. I wish they had picked a more obvious one. But what happens is here we have the constant variance assumption is not met. The problem with constant variance or non-constant variance is that our line of best fit here does a reasonable job of predicting new values, right? Because the values are close to that line, Whereas then as we move further and further out, right, it does a poor job of predicting new values. But so here, oops, non-constant variance, just because the one that they gave us isn't that good, right? If we have, do you want the original plot or the residual plot? Maybe let's do the original plot. So here's a line, and my points might go something like this. That is my line of best fit, right? There's no other way that I could slice and dice that, right? I'm gonna fit a linear model to it, okay? But what happens is down here we have reliable predictions. And up here for this range of x, right? So here between these two values of x, I have very reliable predictions. And then between these two values of x, I have unreliable predictions. Which we can't really handle, right? And so what that would look like in the residual plot, so here's your y and here's your x. Your residual plot around 0, and your x would look something like this, and it would just amplify that kind of explosion, but it would look the same. So this is where I was super confused. Why do we need residual plots when I can just look at the original scatter plot and essentially tilt it on its side and put it to 0? That is what it's doing, right? But it does magnify things a little bit. So the problem here is that we shouldn't use this model because it's not clear to us, right? There's nothing in the model that says, whoa, are you putting in a value of x that's large? I can't handle that, right? This prediction is not going to be very good, whereas this prediction would be very good, right? For small values of x in this case. Okay, there, that's residual analysis. You'll need to do some of it on the assignment, but none of it on the final. So there you go. Done. Check. It is kind of fun. Once you get into the groove of things, then residual analysis is kind of breezy. But where's my next page? Not for a while. Let's do 8.2. Least squares regression. And I know I'm running out of time. But what I want to do is I want to grab just want to show you or start the example where we're calculating the slope and the intercept. So we're going to talk about this, or we're going to use data from this example here. And so it's about gift aid from the university against the family income, right, of a student. So Elmhurst College in Illinois, gift aid is financial aid that does not need to be paid back as opposed to a loan. And so as the family income increases, the gift aid decreases, right? And so we have a strong negative linear relationship, right? So let's start there. Start with what we know. So here I'm going to say we have a strong negative, oops, linear relationship. Oops, there. So what we're gonna do, oh, here they talk about blah, 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 the conditions, we already did that. Where is it? Here. So there's either this, I actually prefer, and they talk about how they arrived at these formulas, but we'll skip that. I actually prefer the formula sheet. Well, no kidding, I made it. Can make whatever I want. So this information here is the same as what we have on our formula sheet, just a little bit more detailed in case you're curious. But what we're gonna have is now I'm gonna give you all that information and we're gonna calculate the slope and the intercept. I forgot that it does that. Okay. So what I said was, okay, I'm gonna have to give you a ton of information or a ton of different information, right? Need to give you the correlation, right? And the correlation is here and it is negative. It's not as strong as I thought it was gonna be, but that's okay. I need to give you the means for X and for Y, the standard deviation for X, the standard deviation for Y. And so here, right, I have given you all that information that we need. Okay. So now we're going to calculate the slope. The slope is the correlation times SY over SX. Here they've been really generous with notation, right? Telling you which one is X and which one is Y, right? This could just as easily have been in a blurb, right? Where the mean family income is 101,700. The mean gift aid is 19,940 with a standard deviation of 5,460 with a correlation of negative 0.499, right? So it can all just be in a blurb and that's usually how it is. But here they've highlighted what everything is because it's our first time. So now we're in a plug and chug type of situation. So here, negative 0.499 is the correlation. I have that in the table. The standard deviation of Y is 5,460. And the standard deviation of X is 63,200. Do I have these somewhere? Nice. So it is negative, which checks out, right? Because it has to be negative. Our slope needs to be negative. So negative 0.043109811013. Okay. Now we can use that to find the intercept. The intercept is Y bar minus the slope times X bar. We're given Y bar is 19,940 minus negative 0.043109811013 times 101,780, I want to say. And I've got it here pre-baked. I am going to be really careful here with my negatives, and I'm going to put in this step for anyone who's not terribly comfortable with math. 0.716475, which puts me at 24327.71647. Construct the least squares regression line. Sounds hard. It's not. Y hat is B naught plus B1 X. Y hat, we found B naught. 24327.72. Let's round because I'm lazy like that. Oh, but the slope is negative minus 0.043. Sure, 1 times X. Or if you prefer, with my last few minutes here, the predicted gift aid, you can put a hat on top, is 24,327.72 minus 0.0431 times the family income. Now you can put in any value of family income and predict the amount of gift aid that you would get. And now you get to go and have a wonderful long Easter weekend. See you guys on Tuesday. Stop this recording here.